Okay, we're going to be brave and try PowerPoint. PowerPoint last week crashed like 3 times on me. We'll see. So Rocprof-sys is the next tool you may want to use. It's collecting a lot of the same information as Rocprof-v3, but it's going to add to it everything that's happening on the CPU. Particularly when you start doing MPI, you're going to see these long gaps between kernels, and you're going to wonder what's happening. You've got to know what's happening on the CPU. You may have something like somewhere the ROCm software is causing a synchronization on the CPU that you aren't expecting and causing delays. So this is really crucial as you try to move to a system level view of what's going on. So here, Rocprof-sys, we're going to do a run command and generate a profile. There's more options here with the latest release. They keep adding features. So Rocprof-sys was started by John Madsen out of, I believe, Lawrence Berkeley. He wrote the TIM memory tool while he was at Berkeley, and he's integrated that also into this tool. So it's collecting all sorts of information. And it's a little hard to tell at this scale, so you may want to look at the slides for this section. But it's showing all sorts of timeline information here. And what we see up here is the call stack and what it's measuring here, but everything that called it. So you start to get an idea where in your program this kernel is what routine is calling it. So it shows here we're seeing the frequency, and you can see temperature. Usually I suppress those because unless I'm worried about the thing overheating or some downclocking, I'm not going to worry about those. But there's a lot more information here, and you can pin up here with the ones that you are most interested in. So down here, it's even hard to see it here. So we're starting to see some activity on the GPU here. So typically what we do is we first configure the system for what data we want to collect, because there's a lot of options. And so you generate the output of with -G, it's going to give you a list of all the things you can collect, and you can select which ones. Then we're going to instrument the binary. You can actually do instrumentation on the fly. I do not recommend that because we find, especially with MPI, that it may take too long and it will crash. So we pre-instrument the binary by running the Rocprof-sys instrument and generate a new output executable. And then we're going to run that. And then we collect the trace here with Rocprof-sys run. This is the configuration file. It's a full screen full of options that you can set. And it takes some experimentation. There's some I turn off, like there's a way to turn off getting the temperature and the frequency on the GPU. I usually don't worry about that, so I don't want to see it for every GPU. But there's other things you can turn on. So you can turn on MPI profiling, OpenMP. They are integrating now the OpenMP, OMPT level data collection, which is the official standard of how to collect data from OpenMP code. You can do sampling if your hardware counters are blocked. So does everybody know what the paranoid setting is? So on your node in the operating system, there is something called paranoid. And it used to be from 2 to -2. And if they set it to 2, you were not allowed to collect information. So we would reset it to 0. Some sites get paranoid about it. That's why it's called paranoid. It's really hard to see how anybody could use that information to understand what you're doing on the system. So it's kind of ridiculous that they block it. There are ways to change that setting in your Slurm script that people have done. You can also, there's new ways to set a group who have access to those hardware counters. What is particularly bad is Ubuntu just added a level 4, which blocks everybody from accessing anything. So it's becoming more important to be able to change that setting. It's really easy to change. It's just, and sometimes we would ask the system administrators, give us a special queue or a special node where we're allowed to collect data. Okay. If you don't have that, you may want to turn on sampling. So what does sampling do that is different? Well, we've been talking about hardware counters where it's collecting it from something on the system, a count that the hardware designers put there to count how many things happen. Sampling is going to interrupt your program at predetermined times and say, where is my program counter? And by collecting that, it can give a pretty good statistical estimate of what's happening on your system. And it can also give you that call tree. So that's always useful, even if they have set the paranoid setting very high. So you can go through these and see which ones you may want to try. Collecting too much information can cause some difficulties with just so much data being collected if you've got a longer run. And you can set your file that you want to collect and use this variable to set where you have that file. Otherwise, it will do the default. Okay, so first, you may want to try that. So if you're on AAC6, go ahead and do a module load of the Rocm and just do this Rocprof-sys avail and look at all the different configuration options that you have available. So that's the first step. Now we do that binary rewrite where we're going to instrument our executable. And so here we're generating the Jacobi hip.inst for instrumented executable. There are some things you can do to customize this. It skips shorter routines. So you can configure, and the reason it does that is it adds too much overhead if it's a small routine. So you can change which of those small routines get instrumented. Generally, it makes a smart decision there. Now we run the instrumented binary. So we're going to take that .inst and we're going to run that file. So we see down here we're running that Jacobi hip.inst and we're getting a profile output from it. And it should give you this kind of output. If it's not, you may be hitting a case where there is a bug in the profiler, and we are trying to trace down all those bugs. So that's something worth reporting when you have that issue. It's going to show you where it's putting out the output trace. And now we're going to we can look at some text output, which is basically showing either the flat profile or the hierarchical profile of your kernels being run. This is generated if you turn the profile true. Here's the flat profile. So it's going to list every call to that routine in one line. The other one shows the call stack to each call. So they give you different information, just like the standard Unix or Linux profiler commands. Sometimes you find one view of it more informative than the other. So here we're seeing the total runtime main, and then we see a list of the routines and how much time they're taking. And self means that how much time is in that routine, and we can see the sum is 82 here. So we're looking at the top routines here. And we're also seeing how often they're being called. So this is the flat profile version. What we usually use Rocprof-sys for is to look at the timeline traces. So here is the output, and you see a lot of CPU frequencies here. So we can get CPU frequency, GPU information, and we see the call stacks up at the top. Now that we download that file and we open the trace file in Perfetto. It can be very easy to get files that are too big for Perfetto, and we can deal with that by reducing the amount of information, or we can launch the trace profiler first and then attach to it in the browser. So here we're seeing the CPU functions, CPU metrics. We can zoom in like we did with Rocprof, so we can use W, A, D, and S to move right or left or zoom in and out. So hard thing sometimes is to get to the routine that you're interested in, because there's too much detail if we're zoomed out. So we want to zoom in on the part that we want. We're seeing more things over here that you can record: page faults, memory, how much memory we're using, GPU temperature, and we're seeing the flow events, so we can see what. And here, this is kind of interesting when you see something happening on the CPU that is blocking something that can happen on the GPU. So especially when you start doing MPI, where are you being blocked? And are you really overlapping your communication and computation? We can select the metrics we want and pin them to the top, clicking right here. just to the right of the field. Here, this is looking at an overlap of compute and communication. So what do we see here? We see the MPI receive, the send. This isn't our ghost exchange. That's the same problem we looked at earlier. And we can see what HIP activity we have. So we have, this is our blur kernel. So that's a kernel. And we see the send receive being done at the same time. So that's confirming to us that we are overlapping communication and computation. So you can see that this would be an interesting view to look at that HIP version and the OpenMP version. What is happening between those two? Is it the kernels taking longer? Is it the communication? But you know, when you get to that level, it's really important to see the combination of what's happening on the CPU and the GPU. So that's what we primarily use Rocprof-sys. What is happening in the gaps? You know, I got a gap here. I know this is keeping the GPU busy, but what's happening in these blank spots? And even when you use Rocprof-sys, there's still some blank spots that we puzzle over. Why isn't it doing something? And it may be something low level on the GPU or the CPU. And trying to dig into that can be really helpful to understand what's blocking the performance, why we're not getting as much performance as we're expecting. Okay, so that's the number one case where we use Rocprof-sys is when we add MPI. So we're getting the MPI information. So we use Rocprof, we're starting to use MPI. We want to see what's happening with MPI. Okay, the second case that is most common that we use Rocprof-sys, that one's coming up here. And this is streams. So we're launching multiple streams here. Here's one stream. Now we're launching two streams. So we could actually break up our array and have different streams operating on it at the same time. So this is another level of parallelism. We already got 1,000 level, parallelism we can do on the GPU, but now we can add streams as if we need more. But this can be really effective to deal with, let's say, a key blocker in a solver kernel. I just split it up among queues. And you can see the communication here and the computation. So we're bringing information to the GPU, large compute, and then copying it back. Here we're doing two queues. What happens quite often is you write this code and it's no faster. You're going, what's happening? And then you realize there's something that's serializing those queues. And it's only when you look at Rocprof-sys that you can figure out what is causing that serialization. It could be something like a memory allocation that you don't realize is happening. Okay, here we're going to 4 hardware queues. So this is showing we're getting good overlap between the streams. You can only launch as many streams, to launch more streams. If you're using too many vector registers, it won't launch additional streams. So it has to be a kernel which is pretty optimized. And so you see over here on the right, by doing this in this analysis, we were able to get, for 4 streams, we were able to get a 3.5x speed up. So that can be a very effective way to get some speed up on your system. And Rocprof-sys is really, really important to understand what's happening, because otherwise we have no way to tell. Why is it serializing? Here's a sampling. So in sampling, we can get that call stack. So we see Jacoby is calling this routine that is where it's showing the time being taken. And it could be that you have a kernel that's being called in two places, but we want to know who is calling it. So the call stack is really effective at finding that now. And you also see it's calling things you're surprised about. Why is it calling that? And so that can be helpful to maybe understand some of the overhead that you're having in your routine. So here we're doing a create mesh, Jacoby. We're initializing, setting the memory. And then you can see some of the things that are happening down at the lower level of the software stack in Rockem. So we see get PC bus ID. So you're starting to see a lot of the lower level support routines within Rockem. Any questions on the sampling? So this can really help you understand maybe some overhead, maybe give you ideas how to reduce it. So if you see this and you didn't realize you were initializing the memory, this may give you a key information that I could get rid of that because I'm going to initialize it later. So we can zoom in on that call stack, and it's really hard to see these things until you zoom in a little bit. We see kind of a whole bunch of string calls here. Why is it doing that? Well, it does have to do those things in some cases, but it can help you understand the overhead in your code. Maybe eliminate it. Okay, this is some new support in Rocprof-sys for network performance. You remember we said that data movement is really key to a lot of our performance, and so they've actually recently added information about network. What's happening on the network. So this is using PAPI counters. And you might want to, if you suspect that network performance is important in your application, you may want to look at that. And you can get then network stats out. So what do we see out of this? We're starting to see the activity across the network, which is pretty amazing. And that's from Rockem 6.4 on. We do hit errors with these tools, Rocprof-sys and Compute, because they are so powerful and do so many things. We do hit errors with them quite frequently. The key thing I want to point out here is if you get a very large trace file, you can launch Trace Processor on your laptop or workstation first, and then start up Chrome, and it will give you an option to load that file. So that can be really helpful because the file size, 4 gigabytes, sounds large, but not for trace files. They can get large very quickly. The other thing you can do is to reduce some of the options you're doing and to reduce the amount of information that's in that trace file. OpenMP, we're adding more and more support for OpenMP. I think right now they're working pretty hard to get the Fortran traces with OpenMP into the tool, into the profiler. There's some special support here for COCOs. It's going to shorten the names of the routines to make it easier to do analysis. We work really closely with the COCOs teams at Sandia, so we have special support for that. We also support a lot of the Raja performance tuning. And here we're showing the Fortran OpenMP coming in ROCm 7.1, so quite soon. And we have quite a few exercises with Rocprof-sys to sort of see what's going on. So for the ghost exchange is something we want to take a look at and maybe do a comparison between the HIP and the MPI versions. So you're going to load ROCm. So Rock Profiler systems, we set the path to that executable when you load that module. I don't think it's strictly necessary if you have ROCm loaded. Any questions on the systems profiling? There's one I really, really recommend running it, and downloading the trace and seeing what you can see. And if you hit any problems or having trouble getting output, that's where these training sessions are really, really important, because it can take a bit of effort to get the output that you would like to see.
What does Rocprof-sys use causal do?
Causal was a research project where they were basically perturbing, just inserting little delays in different routines to see which ones they could speed up to get the most effect for the overall speed up.
Okay.
It is a heavy research project. I don't think it's valuable right now. And there hasn't been much work on it because Jonathan Madsen got promoted to head the whole profiler team, and so he hasn't been working on it as much. It's an interesting idea because you can speed up some parts of, let's say, the HIP call stack, and it has no effect on the overall runtime. So which parts matter? In your application, you're only usually doing one thing at a time, so it's not as useful for your application.
But when you output a call tree, for example, and with timings, does that for a call, or there's a total timing, right? Or
So in the call stack, it's going to be showing the timing for the routine at the bottom.
Yeah.
And then you just want to know what called it.
Yeah. So the point of this is to see how many times was it called, right?
Yeah.
Yes.
So what the causal does is it charts, there's multiple things happening. Yeah. And it could be that one, what is the critical path in project analysis? You figure out, if I build the wall first and I speed that up, does that speed up building the whole building?
Yeah.
So it's trying to do an automated analysis of that, to figure out where you should spend your time speeding things up. And Rocprof-sys is heavily used by some of the teams that are working on, let's say, the Gordon Bell Prize submission. They want to know where their time is, what's holding things up, and where they're getting overlap so they can optimize things. So you might get an idea, well, looking at this tool, why they rushed it out of our research group into production, into the Rockham distribution. It's really crucial information to understand what's going on. On this page, they're looking through the stream example, stream overlap, and it comes out of the HIP book, the basic example. But as they studied it, they looked at, you can set the maximum hardware queues on the system. The default is 4 CPU maximum hardware queues. So if you can set it up as high as 8. And similarly, if you're doing multiple MPI ranks per GPU, you may want to increase that GPU max hardware queues. We see an example here where they look at pageable memory versus pin memory. Does everybody understand what pageable memory is versus pinned and why we want to use pinned? So if we're going to send information over the network or over the PCI bus, we have to pin the memory so that it doesn't get page swapped out during the transfer. Okay, so if your memory buffer is not pinned, it's going to have to copy it over to pin memory and then send it. So if you're going to be moving data, you want to do pin memory. And this example shows the difference between those two. And they spent a lot of time putting these examples together to show interesting information with the tools. So if you go to the 2 pageable mem directory, you'll see the difference between pageable memory and pin memory. Here we're getting the output from Rocprof-sys available and all the options that you have. If I make that larger. So we'll ignore the causal because that's more of an experimental option. We can add the PAPI events. We can add sampling, different options for sampling. Modify the tracing. Add COCOS if we want to, MPI, profiling. And we can get data from Rockham SMI, which is going to give us more information on the time or the frequency and the temperature of the GPUs. See, the default is sampling is false, so you may want to turn that on. If you do Rocprof-sys instrument and help, you will get more information than you probably wanted. And then if we do the run command. Not tight. We also see we get a tremendous amount of options that we could look through, see if we can customize what we're getting at. So we can see here, we can get information about Rickle, OMPT, which is the OpenMP tracing interface. And we can customize even packages like PAPI to get different kinds of information.
When I do Rocprof-sys run, it says even paranoid level is at 4.
What node are you on?
BL1 S24 60.
16.
Yeah.
I just set all those down to 0.
Oh.
Somebody keeps resetting those. I want to work with our tools team to add this group that so that we're handling that properly.